Okay, thank you much, and good afternoon. My name is Joe Labono, and I'm currently serving as the lead engineer for the Bayonne Bridge project. The design team is headed by a joint venture of HDR and PB, and I serve as the lead engineer of that joint venture for this project. It's a pretty interesting project, and it's a case where an 80-year-old arch structure was able to be strengthened, rehabilitated, and a new floor system put on it to give it more vertical clearance for future shipping dictated by the needs of the widened and enhanced capacity of the Panama Canal. So we're going to go through a few things today to show you basically the work that we've done. It includes quite a bit of computer analysis, arch strengthening. We had to cut new portals into the existing wind bracing of the existing structure. We also will talk about our role where, given the complexity of the structure, we actually provided the design for the temporary works for the contractor. We'll talk about the construction of the new arch floor, and then I'll show you some pictures of the construction where we're a little bit over 50% complete after a notice to proceed in May of 2013. So, just a quick background on the bridge itself. It was opened to traffic in 1931. It's a design by Akbar Aman and Cass Gilbert, who also did George Washington, Triborough, Whitestone, Throgs Neck, and Verrazano Narrows. So the Bayonne Bridge has some pretty good DNA in its background as to the designers. It was opened in 1931, 1,652 feet, pin to pin. And at the time, it was the longest steel arch span in the world, and it remained as such for about 46 years when it was overtaken by other bridges. And today, it's I believe currently fourth on the list of longest span steel structures. It was designated for a civil engineering landmark in 1985, and New Jersey entered it in their historic register in 2001. Here we can see the original construction and some black and white photos. Pretty typical with a top chord crane and some tiebacks, and here they're lifting the panels of the flooring system on the lower left. On the right, they were building the approaches with some pretty massive piers and a two-girder system, which we'll see the cross-section here shortly. Anybody that has an interest in these 6 bridges, as they're called, there's a very nice book. It's out of print, but it can be obtained from places like Amazon, which gives you the history and the linkage of these bridges all together, all in the New York City area. Move that. So the existing facility is about 7,000 feet long when you combine the approaches in New York on the left and New Jersey right. And the bridge itself spans over a shipping channel called Kill Van Kull, and that's the entrance to the the container facilities. And if you look in the lower left-hand picture, that's just a barge, but the container facilities are to the right on the other side of the bridge. The Bayonne Bridge connects New Jersey at Bayonne into a borough of New York City called Staten Island. You can see the Bayonne Bridge down there on the southern edge of the peninsula going into Staten Island. The big interest in the Bayonne Bridge, it only carries 22,000 vehicles a day, but it happens to be in a location where we can see the shipping patterns for the containers come in from the lower bay of New York, which is on the right, and going under the Verrazano. And then it goes under the Bayonne Bridge and it heads towards Port Elizabeth and Port Newark, which are the container facilities. So all traffic going to Port Elizabeth and Newark needs to go under the Bayonne Bridge. The current, what's called air draft, is 151 feet. The water draft was recently dredged to a 50-foot depth. So the expansion of the Panama Canal, we're going to have bigger ships. The design is for 215 feet for Bayonne. The newer ships, the 13,000 container ships, are going to be about 200 feet in height above the water. The Verrazano Bridge, which they must go under first, is around 220 feet currently. So here's the cause and the reason for the project. We have basically a service of 5,000 TEUs. A TEU is a term to denote a container. And we're currently servicing 5,000 TEU ships at the port. And we're expecting now to go to 13,000 TEU ships, which will require the 215 vertical clearance. If this was not done, then obviously it's got some economic impact to either the shippers or to the end users of the products coming in and leaving the port of New York. So here you can see a graphic of the changes that we're making. Red line going through the ship is 150 feet approximately above mean water, and we're taking it up to 215 feet at the center line of the channel. So here we can see it expressed graphically. We have 151 foot today. And you can see in the background of that first photo, or the left-hand photo, the container facilities in the background, and in back of the container facilities is Newark Airport. The proposed project under construction now takes it to 215 feet in a combination of rehabilitation, retrofit, and reuse of the existing arch structure. So the project description for the design, we added a 12-foot shared use path. We put in median barrier, put in shoulders on the approaches, acceleration and decelerations, a whole new power and communication system, new tower structures, which are the interface of the approaches and the arch, mechanical electric buildings in both New York and New Jersey, a big storage facility building in New York, and the new towers that we're building will have new electric service as a distribution point. And we also put in a closed drainage system. The existing bridge just dumps the water over the side, which now we're collecting it and moving it to retention and filtration ponds. The arch, excuse me, which is the main feature of the project, doing quite a bit of work. We're strengthening the arch to take the new loads, putting in an entirely new floor system with new suspenders, put in an edge girder system, which we'll talk about, which supports the hangers, the suspenders. We're doing repairs that were part of the biennial inspection. As well as the construction goes on, we sometimes will uncover some issues that need repair that were not obvious in a biennial. Putting in a health monitoring system. The bridge has already been abated for lead paint. We performed a hands-on inspection. Smart Bridge is part of the health monitoring system, which will also include work like alarms for ship impact. There's been some mast hits on the bridge, and we'll be now alerted with that. And then obviously there's some demolition work to get rid of the existing arch floor system. The approaches are entirely new foundations, columns that are precast segmental, new superstructure, which is also precast segmental, and then a complete demolition to 3 feet below ground of the existing substructure, which is pretty massive. in addition to removal of the two-girder system that is the superstructure. Here we can see an in-depth inspection by our staff, assisted by people with certified level 1, level 3 climbing. Our inspectors were certified level 1, so we had professional assistance in doing a hands-on inspection of this arch using rope access for the most part. Here you can get a little sense of the size of the project when you see that person climbing up the suspender system on the left, and then walking across the top as a container ship is leaving port and heading out to sea. So the approach structures in New York, we have 12 spans of new segmental, and in the background you can see the old approach structures. So we took out more than half of the piers in the new design, and those piers now, or the new piers, actually open up the area under the bridge quite nicely. In New Jersey, we have 14 spans at the low end. We're running anywhere from 125 to 171 feet, but as you get to the taller spans, we're ranging from 252 to 272 feet. So it's a pretty diverse range of spans, but they're all being erected and constructed using precast segmental erected by balanced cantilever. And we'll see that. So here's the cross section of the new box girders, side-by-side box girders in the approaches with a 1-foot gap between the structures. You can see the very wide box on the northbound side because it accommodates a 12-foot shared use path. The piers are replicas of the original piers to the best that we were able to do it, so that we're honoring the architecture of the original bridge. Here we can see the 3 types of piers that we had. We had twin single column piers. We had a double pier with a unified cap at the top. And then for the very tall piers, which get up to about 160 feet, we put in an intermediate strut roughly 100 feet above the ground. The construction was rather interesting because we wanted to stay on the right-of-way. So you can see the existing condition, which was just a simple 2-girder system with stringers and cast-in-place deck with floor beams. We actually had to erect the piers segmentally in between the floor system to be able to stay within the alignment and not interfere with the traffic, which is pushed to the left. And then when we get to the final condition, we demolish the existing piers and complete the southbound side, which is on the left side. During the construction, we started with a concept for the tall piers of partially the southbound pier, which is the one on the left in red, with the transverse strut at the lower level. And the purpose of that was to brace the northbound pier on the right-hand side of the third graphic. We worked with the contractor after the bid, and we came up with an alternative to not require erection of the southbound side, but we put in a pipe strut which provided the bracing. You can see on the northbound side up at the top that the box girder loading is eccentric on the pier, so there was a tendency to bend the pier and move to the right. So that's ongoing right now. You can see one of the pipe struts. This is at pier N8, where N1 is closest to the water. And you can see the pipe strut installed and the intermediate bracing that we attached to the precast concrete column to cut down the bending length of the pipe. This is a 60-inch pipe with about 1 3/4 inch wall thickness, and it takes up to about 2,000 kips of load. And here you can see visually what the difference in the profiles are. In the foreground, we have the new segmental box girder. In the background, we have the existing steel two-girder system. And the difference in the profile in this area is approximately 40 feet. So it's a pretty significant difference for the people living in the neighborhoods. The arch, which is kind of the main feature of this project, is it's a through arch with suspenders, and we'll see the specific geometry. But the original design had a sidewalk on the west side, which is the left. We have the arch chords, but one of the problems with the bridge is it had a 40-foot roadway gutter to gutter, and it was simply 4 10-foot lanes, which is obviously a safety issue, and there was no median barrier, so there were the occasional head-on collisions. The new cross section, we were constrained by the clear width between the arch chords and diagonals, and we're able to get a 4'9" breakdown shoulder in. We were able to put in 2 12-foot lanes, a nominal 2-foot shoulder at the median, and then replication symmetrical about the center line. And you can also see that we added a 12-foot shared use path, which will accommodate pedestrians and bicyclists. Here's a nice cross-section extruded of the existing bridge looking north with 4 10-foot lanes, and the new bridge with the same 4 lanes, except now with a median barrier and shoulder. And on the right-hand side, you can see the shared use path. Real quickly, you can see underneath we put a utility gallery where we could run all the conduits and power supply for the bridge. The design addressed 3 fundamental loading cases: the base loading, which is your vehicular, typical AASHTO LRFD loading, and then we also took a look at and included a bus rapid transit with a dedicated lane in the center. And the third option that we looked at and included in the design is an LRT, light rail transit, which would be an extension of the Hudson-Bergen line, which runs about, stops currently at about 4 miles short of the bridge. So the feeling was in the future we should be able to connect the light rail transit to take people into Staten Island from the New Jersey side. So all these were included in the design, and obviously we designed for the worst case generated by those loads. Looking quickly at the original loading from the design documents back then, Amman had the foresight to include a transit load, which he took as a fraction of an E60 loading, and then we had the car loading back then. Live loads have actually reduced a little bit now to 540 foot-pounds per linear foot, but the intensity of the shared use path load has gone up. We had the, looking at the lower sketch, you can see we did include the light rail with a very specific vehicle that's used for Hudson-Bergen. And we're just going through some loading patterns, but by the time you get done, it turns out, because the introduction and the original design of the transit loading, the E60, that the actual loads on the bridge were comparable to the original design, with the big exception that with the shared use path on the right-hand side, we did introduce an eccentricity that was tended to dominate the design when combined with wind. So here we see what we call the non-suspended part of the arch. It's a column system that we're bracing into the existing chords of the existing bridge. We're building a column system that looks very similar in nature. Those are plasma cut plates to replicate the original architecture. And then we have the sway bracing. And then an entirely new floor system at the top consisting of floor beams, stringers, lateral bracing. You can see on the left-hand side a catwalk, which is for utility and maintenance purposes. And on the right-hand side, the shared use path with its own lighting system. And underneath the shared use path, we have a utility gallery where most of the utilities are contained. So a blow-up of the cross-section, it's pretty classical floor beam design with the suspenders either side and the addition of what we call edge girders, because our design criteria required us to consider the loss of 2 suspender sets consecutively. So we needed a bending member on the outside edge, and we included then an edge girder that could take such a load. We're also, just going back quickly, the deck is a lightweight concrete deck. We were fighting load on the bridge, and we wanted to minimize as much as possible. And we used 125 pounds per cubic foot load concrete in the specifications. And they're busy now testing that material because we're not terribly far from pouring some of the deck in the arch. So what the work consisted of is we had existing arch cords, floor beams used as bracing members, and we considered then strengthening in those areas, redoing some bracing, adding columns where we needed to increase the height to a fixed floor system off the arch. And then where we had a suspended span, we raised we put in the new suspenders, and you can see the difference in the existing floor beam to the new floor beam. And we'll go through a sequence how we are able to accomplish replacing of the floor beams, and eventually then we'll be demolishing the existing floor beam at the bottom. So again, just more definition. I actually went in the wrong direction. So the statical scheme for the arch is we have tower structures that bracket the arch structure, and that's really to accommodate the transition from the approaches into the arch structure. Panel point 0 is actually inside the tower structure. For the purposes of the deck, we have deck joints. We have an expansion joint at the south side, panel point 10 south, and we have a pin joint at panel point 10 north. We're able to run the deck over the tower so that the big expansion joints are not near panel point 0, because they've had a history of maintenance issues with leakage running down then on the main verticals at panel point 0. So now the joint will be placed over the tower. Quick introduction and discussion of the staging. So we have the existing bridge with 4 10-foot lanes, and it's a 6-foot clear sidewalk on the left-hand side. So the first stage, we demolish as much work as possible, remove as much dead load as possible to the west side, which is the left side. Using temporary barriers, we're able to take out a lot of, we're taking out the sidewalk, we're taking out some bracing, some steel work, and we provided 12.5-foot lanes for 2 lanes of traffic. This bridge, all during construction, we maintain traffic, 1 lane of traffic in each direction. In the second stage, we're coming over and putting the temporary concrete barrier to the east side, and we're demolishing partially the existing deck, and again, taking out as much dead load as possible. And here we can see some of the staging work. On the left-hand side, you can see temporary shoring towers. When a new approach pier was going to interfere with a new pier, we're able to put in shoring to support the roadway and the edge girder, the existing girders. And we were able to push the traffic to the west as you look at that picture. If you look down on the second side, you can see the deck is partially removed on the east side and one lane of traffic maintained during the construction. Level 3 or stage 3 is we're now where we are currently. We are removing the existing suspenders and getting in the new floor beam systems, and we'll show you the sequence for that, all the while maintaining one lane of traffic on the lower or existing roadway. So right now working on the upper roadway, the new flooring system. And then we go to stage 4 when the upper level is constructed. About half the roadway, half the cross section, we're able to put traffic up top, and we will then proceed to demolish the existing arch floor, which is really the goal of this project because that's what would be blocking the new ships from coming in. Stage 5 then, once the lower floor and existing floor is demolished, we go back up and finish the work at the upper level and complete the roadway to provide 4 lanes of traffic as it was before the project started. Here's a quick video to explain how we worked around the towers, which is, we can see the tower structure. We removed as much material as we could, and we also then diverted the traffic to the west to get clearance as part of the overall traffic staging plan. And again, removing as much dead load as possible ahead of time. We built a new tower around the existing towers to the extent that we could without interference to the traffic up above. We then pushed the traffic to the west side so that we could have access and demolish the roadway slab. There you can see it. And then you can see the new tower structure going in, basically surrounding the existing one. Built the new electrical floor, which is the distribution center for the electrical services. And then we put the new floor system on top. We then proceed to, and we're now getting ready to cast the roadway over the tower area. And then we'll get the traffic pushed up to the upper level, and that would free up the demolition of the lower levels and the completion of the structure, not only for the arch and the approaches, but also for the tower structure. We'll complete the bracing that we couldn't get access to. We'll construct stringers and floor system, and then we'll get the utility catwalk put in, all the finishing work with all the access, and then we'll demolish the existing tower structure and put in the new permanent median barrier and get traffic up to 2 lanes in both in each direction. Talking about computer analysis, the bid set contained 37 sequence drawings for the arch and the tower. We've had 3 revisions to the as-bid sequence proposed by the contractor, and we checked it out for him. Here's just one of the sample drawings of the sequences. You can see they're rather detailed, and they go through many steps, step by step. So that was the blueprint for unloading the arch, strengthening it, and then reloading the arch. All that work was performed by the designers. Here's the arch model with where we had both roadway levels, new and old, and we went through stage construction. Had about 14,000 nodes, 14,000 members. The deck was modeled with plates. We had springs, master-slave nodes, 296 sections, 544 static load cases. We had 38 construction load cases, including 349 construction steps. So it was a pretty significant computer effort. This just tells you all the work really that we did going through this thing step by step. The only thing that was time dependent in here would be the concrete, where we would have creep and shrinkage and strength gain with age. We were able to calibrate the model geometry with survey data, so we got good response correlation there. And we provided the stage construction results for geometry control and the determination of cambers for the new members. The really big work here in terms of difficulty is arch strengthening, and the three main areas were the end vertical, where we had a lower chord, where we had most of the new forces coming in. At panel point 10, we had a new, and around panel point 10, we had a new portal to cut in. And at the center of the bridge, we had some strengthening work for the section which had actually the least amount of compression in it. In the lower left-hand corner, you can see your typical detail, which involved the addition of what's called cheese plates to fill in the gaps to cover the strengthening plate, if we call that layer 2 in red. And then in some places where we need even more strengthening, particularly near panel point 0, we had a third layer of strengthening, which would be represented by the blue color. You can see that the existing member was a built-up section using angles and cover plates. And on the taller elements of the lower chord, we had an intermediate internal plate. So there you can see the picture of them working on the existing plate with the rivets in it, layer 2 and layer 3. The cheese plate, which is layer 1, is already swallowed. So the total statistics, the lower chord, 32 of the 80 panels were strengthened. Upper chord, only 8 of the 80. Verticals, 24 of the 82. Diagonals, 8 of the 80. Lateral bracing, 20 of 144. And lateral struts, 10 of 78. So approximately 25% of the structure had to be strengthened for new loads. And a lot of that was due to the wind loads created by a higher deck or a taller deck above waterline. And here you can see a blow up of the cross section with the cheese plate in yellow, web strengthening, then in red layer 10, layer 2, which is the major strengthening. And in certain areas where we wanted to keep the steel plates less than 3 inches, so when we needed more, we actually added a third layer, which would be represented in blue. We're basically knocking out the rivets one by one and replacing them with high-strength bolts. Most of the bolts are, well, depending where you are on the bridge, the typical bolt is 7/8 of an inch, but we do go up to 1.25 inches in certain areas. But they're all high-strength bolts, generally 325, but certain locations they are 490s. And then on the gussets, the lower chord that we see here is not continuous through the node. The plates stop where the diagonals and the verticals come in. But for continuity of the strengthening, we had to put in splice plates across the node, and then we had to put in increased strengthening plates to connect strengthened diagonals and verticals. So there's well over 1 million bolts on this project, and it's just very, very tedious work. But it is what it is. So here we can see them erecting a steel strengthening plate. That's level 2 and level 3 in one shot. And these plates are roughly 12 feet, 10 feet deep. And depending on your panel length, they could be anywhere from 30 to 42 feet in length. So it's a major addition of steel. And just a look on the outside, looking in, you can see splice plates at the nodes, strengthening of verticals and diagonals. So roughly total project has over 10,000 tons of new steel, including the floor system. The new portals, you can see the cars and the existing picture going through portals. Obviously, they need to traverse through the cross-frame system, so we put a portal in. And now we have to move up the arch to a much flatter location to cut a new portal into the structure. And we designed all the sequences and step-by-step, a 12-step approach to accomplish that work. And here's a quick video of the portal sequence, where you can see starting out the existing to the left, and then adding in strengthening of verticals and chords, putting in new bracing, temporary bracing, building the new portal framing, and then removing some of the lateral bracing to accommodate the cars in the new configuration. And here we go to the lower chord portal with its bracing. And all these stages had temporary bracing to keep the structure stable. And then we finish up, with a new portal at an upper level, flatter level along the truss, along the arch. So the temporary braces, as I said, we had a 12-step sequence to adding. We designed and detailed, or we designed them and the contractor detailed the connections and the geometry to work out sequences to allow certain members to be either removed or strengthened. And it was all detailed in the bid set. Contractor came up with some interesting ideas, and here's one that we call the banana gusset, which enabled you to straddle a cord and work then to take the force out of existing horizontal members, either sway bracing or cord connection members. So you can see in plan view that you attach this to existing members and existing cords, and then you can detension the part between the banana and the cord and do a strengthening or put in new splice plates. And the contractor actually came up with this. We did the design, and of course we have to run finite elements to show that the stresses are okay and the sequences. And here you can see the banana gussets in action, where we put them above and below the cord. We're able then to frame in existing lateral members to enable remediation work, either strengthening or gusset additions. And that all worked very well, but again, very time consuming. The new arch floor, this is a concept that we came up with and put in the bid set. Contractor tried to come up with a better way of doing it, but finally came up to the conclusion that this is kind of the way to do it. So we originally showed a gantry crane on the top, similar to what was used for the original construction. They eventually decided to go with cranes on the existing deck, but in principle it's the same thing. So we have a top cord, or a cord member with a hanger to a floor beam system down below, and we push the traffic to the west or to the left and demolished the roadway slab. We then put in what we call transfer girders, and they span 3 floor beams. They span actually 2 floor beams with a floor beam in the center. So if you look at view A, you can see 3 floor beams in cross section, and these are roughly 41 and a half feet center to center. So we span the outer existing floor beams. We then put in a jacking system to take the load off the middle floor beam. And when that floor is off, and here you can see the system, basically a cradle, to pick up the reaction and transfer it to either side. And once the transfer girders have the load removed, we can then remove the existing suspenders. And we can erect the new floor beam at the higher level. We then connect the permanent suspenders to the cord down to the floor beam. And we put in temporary suspenders to replicate the support of the existing floor beam at the lower level. So that enables us to keep the construction process moving. This is done floor beam by floor beam. And then the upper level, they're now they will be putting in stringers between the floor beams, and they'll eventually cast the lightweight deck about half width to enable the cars to go up top. And at that point, once the traffic is transferred up top, we can demolish the lower floor beam. The contractor, we showed actually a box girder for the transfer girder, and they came up with a truss design that they produced, signed and sealed and fabricated. We checked it, and they came up with this truss, and you can see the blocking against 3 consecutive floor beams, and the center of one is the one where the jacking will occur, such that you could remove the suspender set. It's a 4-wire rope set that holds up each floor beam on each side. So to give you a construction update, the Port Authority of New York and New Jersey measures things quarterly, so we've spent approximately $700 million through December of 2015. We'll get the update in April for the spending, but there's approximately $495 million of construction in place. The bid was approximately $750 million. So we're pretty well advanced on the construction, at least on the northbound side. The foundations are all in for the northbound roadway. The columns there's only 1 column now left to erect. The abutments are complete. Steel fabrication virtually complete. The strengthening as of this date is more like 95% complete. The tower construction is complete, except for some final bracing that needs to go in. The approach spans at the time were 50% complete. They're now more like 2/3 complete. On the upper right, you can see a shot at night of the lighting for the work as we go from the tower out into the main span. And on the bottom right, you can see the self-launching gantry that's used. Since it's very close to active traffic, all the erection of the segments are done at night. The bridge is closed and the segments are erected. And then the bridge is reopened after the segment erection has taken place. Here we can see the approaches, which are drilling in drill shafts of 6-foot diameter. The range down to bedrock is anywhere from 15 to 35 feet. So the rock is fairly close to the surface. The erection is by self-launching overhead gantry, and the pier tables, though, are erected by crane. And here we can just see some shots of the erection. The segments, the precast segments, are cast in Virginia by Bayshore Concrete, and then they're barged. Anywhere from 12 to 18 pieces are barged up to, from Cape Charles, Virginia, about 350 miles, to Jersey City at Ports America, where they're offloaded with a big swivel crane and put in storage and hauled over to the site as needed. This was setting of the first base segment on the lower left. And here you can see a precast pier, low, short one, at the beginning of the project that's already erected. You can see the joints to represent the precast segments. Here you can see the shipping from Ports America and Jersey City to the site. All that was planned out ahead, and utilities adjusted as needed, and where stress calculations for load ratings, that was all done by the contractor. Here you can see the pier table being constructed with the first pier segment, and that's being done by cranes. On the right-hand side, on the upper right, you can see the actual self-launching gantry, which can go pier-to-pier and support the weight of the segments coming in from the back of the gantry, moving forward on the gantry. Again, more erection of a pier table. So the first 3 segments were erected by crane. The pier segment itself, and one on either side, is done by crane, and then the gantry comes and erects the balance of the cantilever, which can go up to 15 segments either side of the pier. Here we have some of the steel fabrication, which very interestingly was done in Italy, and very, very good quality fabrication. We did have to make some conversions to Euro code to make sure we had the strength that we wanted. But here you can see some of the tower pieces and some of the column sections, which are cut to mimic the look of the lattice work on the original design. Here you can see some of the column sections, the tower sections in storage in Italy before they went on the barge or on the ship. Here you can see strengthening plate work, which these are cheese plates which fit over the existing rivets so that the strengthening plates can be at a constant location along the cross section. Here you can see some of the tower work where we put new pedestals outside the limits of the existing tower, and you can see them fitting the new column sections onto the pedestals and being bolted into place. Then to get the major part of the column in, it was actually done from the deck level, and where necessary, holes were drilled actually through the deck to drop the columns in. And here you can see the columns going up above the deck level, and you can see on the right-hand side the columns at their finished level for support of the floor beams that will go up on top of them. Here you can see the addition of new gussets to increase or add in columns that will splice into existing columns below. And this is for the non-suspended part of the arch. And here you can see the columns being added to the upper chord to get us up to the new level of the floor system. That'll be what we call the non-suspended portion of the arch. And here you can get a shot from the side so you can see the new tower on the left and the new columns being added to the top chord spliced on with strengthened gussets. And you can actually see some of the transverse floor beams going in column to column. And then you can see the edge girder on the right-hand side connecting the floor beams in the longitudinal direction. So the completed project should look like this in another year and a half, at least for the lower roadway. This was taken on the left-hand side with the tower under construction. On the right-hand side, you can see the raised roadway with the new profile in relationship to the arch. And that should do it for today. So I'm going to transfer control back if there are any questions.
Hi, Joseph. I'm gonna take it over.
Okay. Do you have it?
Yes, I do.
All right.
And thank you so much for the presentation. Thank you for sharing about such inspiring work, very complex, but your thorough explanation really great, gave a great details and, in step by step, how the project has been progressed. Thank you very much.
My
And
pleasure.
actually, there were several questions, but then since they're quite last minute, I'm only going to share a couple due to the time being. For the rest of them, we'll be covering them on our webpage once we publish Joseph's the recording of the seminar. We'll be also putting down the questions and answers that are not covered. For today, briefly, Joseph, could you let us know how you evaluated the capacity of the existing truss member, considering the corrosion as shown in the pictures?
Yes, we did about 250 samples of the steel to validate the yield and tensile strength of the arch. It had the original design had 4 types of steel: carbon, silicon, magnesium, and I forget actually what the 4th one was, which actually turned out not to be used. Corrosion, where decisions had to be made to reduce section, because we had a hands-on detailed inspection, we could make those assessments. Where things got maybe more than 10% loss of section, we actually replaced members. So part of the bid set included repairs that would replace corroded members.
I see. What about buckling check? Adding on to this question.
Hang on a minute. I'm sorry.
It's okay.
Yeah. So which one are we on? The corrosioning or?
Yes, and then adding on, what about for the buckling check?
For the buckling check, actually the Bayonne Bridge is the best rated structure in the inventory for the Port Authority of New York and New Jersey. It's in extremely good shape. For corrosion, we made decisions as to how to reduce a section and consider loss of section in a buckling analysis, which was done nonlinear, and P delta, geometry, materials, the whole bit, and basically introduced an eccentricity to represent loss of section where it was needed. But we were pretty happy. Either you had a very bad situation where the member had to be replaced, but if you didn't, the existing bridge was actually in very, very good condition.
I see. Thank you. Was the precast piers post-tensioned?
Yes, they're vertically post-tensioned using bars for the erection process, and then up to 31 strand tendons for the final post-tensioning in the pier.
I see. Well, this question was actually asked by an engineer in Texas. It's more common around the area also. And then the last part that we can cover is, what are the considerations made for completely replacing the bridge? It's more going into, the scoping of it. But why did the PA NYNJ choose to retrofit rather than replacing it?
Well, several reasons. One being cost. A new bridge was at the time roughly twice the cost of what we wound up doing. The other thing, and we did a study that had 41 options, and in those options we had New Bridge. The thing that hurt the New Bridge is that it would have taken us off the right-of-way. That would have put us into an EIS, which was estimated to be 4 years of time. This project is very schedule-driven, given the construction at the Panama Canal and the pressure to get the new ships into the port facilities. So once you went off the right-of-way with a new bridge, new alignment, then we were looking at 4 years. We actually performed an EA, environmental assessment, and that we were able to get produced, reviewed, and approved within 9 months. So that 9 months for an EA fell within the window of feasibility for getting this project done.
Yeah, sure. It sounds like it.
Yeah.
Okay, thank you. Actually, adding on to the second question really briefly, did you also have the post tensions in the transverse direction at the top of the precast
Yes.
piers?
The deck is transversely post-tension as well as longitudinally post-tension.
What about the precast piers at the top?
Precast piers at the top
Uh-huh.
are, yes, they're
Was it?
post-tension.
Uh-huh, yeah. Okay.
They have a protective additive coating added to the top of the pier tops.
I see. I think
Yes,
some people might actually want to kind of want to get into this post-tension peer part a little more. But I'll talk with you later about this. Okay. Thank you so much, Joseph, for your day today. Before wrapping up, I just want to let everyone know that the next one will be on the May 10th. It's going to be regarding Midas and Luce's comparison for a detailed FEA analysis. Yep, so I'm going to wrap it up here today. Thank you everyone so much for your time, and thank you again, Joe. It was such a it was my pleasure working with you. And yep, yeah, we'll talk. Have a great day, everyone.
Thank you.